We are going to start with talking about logistics for the exam. For anyone who was with me last semester, I have not decided to make a sudden and dramatic change. Things are about the same. And for those of you that are new coming in, how it goes is you are allowed to bring a cheat sheet, 8.5 by 11, front side only, and you can put whatever you want on it. I do take it up with the exam just to make sure it's not the exact exam. That's really the only thing I would say anything about. But you get it back once I grade the exams. The exam is in class, normal time, and full amount of time. Exams are usually 10 to 14 questions, and usually a third to a half are conceptual, meaning multiple choice, and the remainder are calculation based, and it is not multiple choice for those. So you can expect a roughly even distribution of points across chapters 21, 22, and 23. It may lean a little more 22 and 23 just because they're longer chapters, but I'm still shooting for getting good coverage of all three. So the next bit is just broad strokes overviews of each chapter, and then I'll maybe say some specifics about what to look at in more detail. I just want to start by giving the philosophy of each chapter. All right, so chapter 21, the philosophy of it is pretty much the things you probably already knew about electricity, the things that you've maybe seen in middle or high school, and that's about where it stops. And so those things are about what causes electrical forces, and that is an interaction between charged objects. Charge is an intrinsic property of objects, just like mass is. And it is due to these fundamental charges, which are the electron and proton charges. Um, like charges repel, unlike attract, and they do so along the line connecting the two objects. And the closer those charges are, the greater that force is. And all of that gets quantified in Coulomb's law a little bit later. So this whole chapter is about how you determine those forces and some interesting ways in which they can arise that aren't just rubbing two things together and holding them near each other. It will largely be conceptual questions for this one because there's not much calculation in this chapter. The types of conceptual questions you can expect are ones about things like on the quizzes, how do you get a positive charge? It comes from removing electrons. How do you get a negative charge? You add electrons. It's never the protons that are the ones moving around. Excess charges are always due to electrons, at least in most everyday objects. Another maybe more calculation type question that you might see is this quantization of charge, just to say there are legal values of charge and illegal values of charge. The legal ones are the ones that are a multiple of the electron charge because that's what they're coming from. Any charge is due to a certain number of electrons, and it's a whole number of them. So if you have a charge of 1.5 electrons worth, it's not possible to actually get that on an object. So questions like which is an impossible amount of charge, and questions like how much or how many electrons are on this charged object. Induction, it's possible for a single question about that, but it's really just things like that first question on the practice where it can still cause forces between two objects even if one of them is not charged. That was the case with the metal can and the PVC pipe. The metal can was neutral, but through induction, it was still attracted to the PVC pipe. Coulomb's law is the meat of this chapter as far as the exam is concerned. I may ask you a question, probably most like this one, because the next example is a lot like what we would do for electric fields, and we actually realized that electric fields are the slightly less work way to go about this, because if you do all of this, you end up getting something that's whatever charge you're interested in the force on times the electric field. So I'll ask those types of questions in chapter 22. For chapter 21, it's kind of simple, straightforward. What is the direction of the net force? And when we get into 22, we'll deal more with actually calculating forces from electric fields. Okay, so I'd say that's main points of focus for chapter 21 are the quantization bit, that it's electrons that are the moving things, not protons, types of charging, induction, friction, and contact. And then the only really calculation-based thing that could arise is stuff with Coulomb's law. Any questions on that chapter before I jump to 22?
Are there? I know you said earlier about what electrons are impossible, and you named one of those. What are there any are there electrons that'll be impossible to make up an object or so?
So the reason there are certain charges that are impossible to get is because they're not a multiple of the electron charge, meaning they don't come from a whole number of electrons. So any number that's not a whole number multiple of electrons is not a possible charge to get. I can get 2 times 1.6 times 10 to the negative 19 as a charge, so 3.2 times 10 to the negative 19 is possible. So is 3 of those, or 4.8, and so on and so forth. But I can't get 1.5 of them. I can't get 1.25 of them. I can't get negative 6 of, or sorry, negative 6.5 of them. I can't get pi electron charges. It can only be a whole number multiple of the fundamental charge, which is the 1.6 times 10 to the negative 19 Coulomb charge of the electron.
Okay.
The big picture of chapter 22 is that it becomes easier at a certain point to separate the idea of a force from what's producing that force. And so when we look at two charged objects exerting forces on each other, we can start to focus on either one at a time and say it's producing something, and the other object is interacting with that something. The something being produced by either charged object we call its electric field. And then we speak of electric force as something arising due to interaction of electric fields. The remainder of the chapter after we've defined that idea is about how you can calculate electric fields for different arrangements of charge, and then how other charges would react to electric fields. So that's the two bits: is how do charges react to external electric fields? What kind of electric fields do charges create? The definition of electric field is based on an actual measurement technique in a sense. And that technique is I can't see an electric field with my eyes. I can't directly measure it in any way because anytime I'm measuring it, really what I'm measuring is an interaction between the thing creating that field and some other object. So the thing I can measure in an experiment is the force between two objects. But then if I come up with a way of removing the charge of my measurement device, meaning the influence it has on this situation, then I can define what's left over as something only depending on the thing we're studying, the Van de Graaff generator, the charged disk, the charged rod, whatever it is. So it's the force on our little measurement device, which we call a test charge, divided by the size of that measurement device in order to remove its influence. Once we have defined that electric field, the electric force comes from saying, well, any other charge will feel a force proportional to that electric field. So I found this by measuring with one single charge, Q0. If I want to find the force on any other charge, we just multiply those two things together. Take the charge you want to find the force on now and multiply by the field that's being produced around it by something else. This is an important point. Charges that are positive move in the direction of the electric field, or at least feel a force in that direction. Negative charges always feel a force opposite the direction of the electric field that they're sitting in. And the way to remember that is positive charges do all the stuff that makes sense for them to do based on the picture. Negative charges, think of the thing that makes sense for them to do and then flip it over, because they always do the opposite of what you'd like them to. There won't be a question like this where it's combining the electric field stuff and kinematics, but you can expect one like this. This is your sort of bread and butter question type for chapter 22 is I give you a few point charges and I ask you what is the electric field at a certain location. I guarantee you that type of question will be on the exam. The way that you approach these is mostly just normal vector addition. The most difficult part really is just getting the vector directions correct. And so the easiest way to do that is, let's say instead of point O, I asked you for the field out here, where I'm drawing this new dot. In order to find the direction of the field for each charged object, I pretend this dot is a little positive test charge. There isn't any charge at that location, but imagining that there is a little positive charge where the dot is helps you figure out the direction of these fields, because if there were a positive charge there, then charge 1 would repel it. So along the line between them, it would push it away, and charge 2 would attract it. So our little pretend positive charge would be attracted towards that -5 microcoulomb charge, and it would also be attracted towards the -3 microcoulomb charge, but it would be repelled by the 4 microcoulomb charge. And those are the directions of each electric field for that location. That's why we say that it points away from a positive charge and towards a negative, because we defined fields in terms of a little positive test charge in the first place. Okay, once you get those vectors, it's vector addition, and then remembering how you calculate the electric field of each charge. Then it's more conceptual stuff. I'd say you can expect about 1 question about field lines, and it would be something to do with which is which. They point away from positive charge towards negative, something along the lines of that question on the quiz where it said A and B have these field lines, which one's positive, which one's negative. That's kind of in line with what you could expect for field line type questions. This will not be on there, but the stuff about the torque on a dipole, really just this singular little block of text, that is a possibility. So when will you get most torque on a dipole? When will you get least? And how do you calculate that torque? The only thing that's important for the ring and disk pages is just the final result, and then the direction that the field would point at the center. So you don't need all the curved field lines. I just need to know if it's a positively charged ring, the field points away on both sides. If it's negative, points towards on both sides. Same for the disk. You just got to know how to apply this equation and then know the direction of the field at the center of the disk. I don't expect there to be a sheet of charge on there. I was asked to do some questions about rings and disks. So this is a decent example for what you might expect, but I would give you actual numbers instead of this more algebraic way. Okay, so I think that's the main things for chapter 22. So quick recap. How do you find the force on a charge if you know the electric field it's sitting in? Do you know if that is going to be in the same direction or the opposite direction of the field? Uh, can you calculate the net electric field due to a group of charges? Do you know what field lines are representing as far as how large the charges are and whether the charge is positive or negative? Can you figure out which way a dipole will rotate in a electric field and how strong that torque will be on it? And then can you apply these equations for the electric field of a ring and or a disk? Any questions on that chapter?
When you said we're tested by the strength of the electric field, are you talking about? Are you talking about does it like follow like one of the like constraints of the electric field, or just like solving it out?
I'm not asking you to calculate anything, but the strength would be like twice the number of field lines means twice the charge is present.
Oh, okay,
So like when we were looking at these, you need a proportional number of field lines.
right.
All right, well then on to 23. So Gauss's law is the hardest bit of this set of chapters because it's the most abstract. And so that's why we kept coming back to this sort of hand wavy conceptual definition because it is the most helpful thing to picture the purpose of Gauss's law. It says for any type of vector field, not just electric fields, but anything that you can describe as having a certain direction in space. Um, if you put an imaginary surface into that space. You imagine dipping a bag into some flowing water, but the water can flow right through the bag without carrying it away. It's an imaginary bag in that sense that the field lines can pass right through it. If we count up how many field lines pass through it, that tells us something about how much charge or whatever other source we're dealing with is inside of the bag. In other words, there's a direct relationship between what's happening on the bag and in the bag. The rest of this stuff is just turning that into a more concise and quantitative statement. And that quantitative statement is what's usually referred to as Gauss's law. And it is that right there. That is what you will come back to and what should guide your thinking for everything in this entire chapter. It is useful because it relates three separate things: flux, field, and charge. If you know any of them, you are likely to be able to find the other two. For instance, if you see a situation where you've got a Gaussian surface, but you don't see any charge inside of that surface, you instantly know what the flux through the surface is. It's zero. Because if this side of the equation is zero, so is the left-hand side. You also usually can say that the electric field through it is zero, but in some cases it's just there's just as much electric field poking out as poking in. That can also lead to zero flux. In the questions near the end with conductors, how we come to the conclusions we do about conductors is just applying Gauss's law over and over. So I will not expect you to actually calculate this integral for anything but that cube example that we have been doing a lot of different variations on in homeworks and in class. I'll get to details on that in a little bit, but the philosophy of Gauss's law is the most important thing for conceptual questions. It relates flux, electric field, and enclosed charge. And if it is not burned into your brain, the equation sheet isn't going to help because you're going to look at this and it'll be there, but you won't know what it's saying. So just remember, it says this stuff in the box, but that's useful because it says if I know something about flux or I know something about the field, I know about the charge inside the bag. Or if I know about the charge in the bag, I instantly know about the flux or the field. Even if the situation looks like it shouldn't be that easy, it is if you just kind of buy into the idea of Gauss's law. I say that for questions like on the quizzes or chapter 23 quiz specifically. All of those questions become very easy if you just say, I don't see any charge in that bag. Field must be zero. Flux must be zero. That answers about 3 out of the 5 questions automatically. But calculation-wise, unfortunately, you can expect one like this. I would say it's similar to this in that it's relatively straightforward. It's just sort of copy and paste over and over, and you change your DAs. I will probably ask you to find the net charge enclosed as well. How do you do that? That's Gauss's law. I will not expect you to rederive any of this stuff. All that's important as far as the exam goes is can you apply these equations? If you see a charged rod and I ask you the force on a little charge I put near it, it's this times the little charge that you've got. Just like with any other electric field, it's charge times field. You can expect capacitors, they're fair game, as are shells. I'll take out balls, and I'll edit what I just said out of this recording. For conductors, you can expect mainly conceptual type questions, which are just based on these properties. They're all summed up right there for you. but at least one of those does help you with problems like this, which would be the other calculation bit of 23. So besides the cube type problems, you can expect sphere type problems like this one and like the ones that were on the homework, and that are in the practice. That's my kind of recap of chapter 23. So I think we are ready to turn it over to practice questions. So 31, we have a Gaussian cube that is sitting in this particular electric field. What is the charge enclosed by the cube? When I do these problems, the first thing I do is try and sketch this electric field. If you're in Calculus 3, you may have already been doing some sketching of vector fields, but even if you're not, you can figure it out because all this is telling you is that at each point in space, which has an XYZ coordinate, the electric field looks like this. So at XYZ equals 0, meaning right here, I could look at this and say it has no X component because there's no I hat. It has no Y component because there's no J hat. It does have a K hat component, and it is 5 times Z squared. If I'm sitting at the origin, Z is 0, so the electric field at that point is 0. And it's also going to be 0 for anything in this whole plane. But what we see is that as we start moving towards positive Z, so going this way, it's going to get more and more and more of a Z component. In other words, my electric field vectors are just going to get bigger and bigger and bigger. So they'll start back here at a certain size. As I move further along Z, they're larger. And then even further, they're even larger. And I can use that to guess what kind of fluxes I should get through each face of the cube. So let's start with the easy ones. Let's look at top and bottom. What do we expect for the flux through the top face of this cube?
0.
0, because the field lines are just grazing that. And if you're not sure why, let's imagine a side view of this. So this is your eye. You're looking on this side of it. You would see the cube, and the electric field lines would look like this. They get larger as you move along. And so this is the top of the cube, this is the bottom, and the face we're seeing from this view would be what we call the right face in the original view. Does that picture make sense?
Yes.
Okay, so yes, no flux through the top. What about through the bottom?
So that'll be 0 too.
Correct. Okay, and what about the left face?
It'll be bigger.
Well, maybe let's go back to the right face of the cube. So looking at this picture, how much flux is through the right face?
A lot.
Not a lot.
I thought the arrows was the flux.
The arrows are the electric field lines. They're not sticking into the right face. They're grazing it. They're passing by the right face.
Oh.
So
So
to see,
go ahead.
let's take another view from the top, okay? You're looking down this way now. You will see the top of your cube, and you're going to see the field lines going like this. And so this is your left face, and this is your right face. Do you see that?
Yeah, I see.
Okay, so
So
how much
does that
flux?
mean that they 0 too?
Yes.
Oh. Okay.
So this one's actually coming out not too bad, but the back and front face, those are not 0. That's where the field lines actually truly are passing through the cube.
Oh,
So
so the field
this,
lines was coming from the back.
yes, towards the front.
Okay.
Okay, so those are really the ones where we got to do a little bit more work. And so what are we expecting for the back face, a positive or a negative flux?
Would it be negative?
Negative.
Yep, because those field lines are poking into the back face. And then what about the front?
Positive.
Positive, because they're sticking out of the front face. And I can even predict that I'm going to get more flux out of the front than into the back because the field lines are larger. They're longer there. The field is stronger at the front of the cube compared to the back. So that's my guesses, are I should just have flux through the front and back faces. It should be positive through the front, negative through the back, and the front face should have more flux than the back face. That's a lot without ever having to do a single integral. So now let's do those integrals and check. All right, so start with the, let's say top face. How could I write dA for the top face of this cube? So just to remind ourselves what dA is, we imagine breaking the top face into a bunch of little tiny patches, little rectangles. And then we just find the flux through each of those. And the integral is the operation of adding up all of those little fluxes over that whole top face. So what would the area vector look like for any single one of these little patches?
Would that be DAJ?
Yes, because for any of them, remember the area vector is perpendicular to the patch. So points out away from the cube. They all point in the j hat direction and have a magnitude or size dA. So I can represent the entire top face by that same area vector, dA j hat. It doesn't vary from point to point on the top face. But what is k hat dot j hat? 0. And for that, here's Yale's cheat sheet. If it's the same two, it's 1. If it's any two different vectors, any two different unit vectors, it's 0. And that's because the dot product is measuring how perpendicular or not perpendicular two things are. If the two things point in the same direction, you get the largest possible dot product. If they're pointing exactly perpendicular to each other, you get the smallest in magnitude. If they're exactly opposite each other, you would get -1. That's all of your possible combinations. All right, so the top flux checked out. For the bottom, what changes?
DA.
It would be negative J.
Yes, correct. So blah, 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 negative dAj hat. So it'll still be k hat dot j hat. So that's 0. What about for the left face?
Negative I.
Yes, because for the left face, we're looking at these little patches. All of their area vectors point out this way, which is the negative x direction. So we use negative I hat. Okay, but what is k hat dot I hat?
0.
0. And then for the right face,
Positive dA I hat.
yes. But again, the electric field is something something k hat. What is k hat dot I hat?
0.
Yes. All right, so these are checking out so far. Now we get to the ones that are actually a little bit trickier. So that'll be the front and back faces. And by the way, I know a couple of you know this, but for the rest who I've not told this to, do y'all know why we use this symbol for an integral? Why we use that thing?
It's an S for sum.
Yeah, that's all it is. It's a squirrely looking S, and it was meant to be an S to say sum up all of the little things. The D means difference. It's the inverse thing. Sum up all the little bits of A changes in area as they accumulate, and you will get the overall thing, okay? And that's the fundamental theorem of calculus is if you add up all the little bits, you get the total change. So pretty smart that people decided to come up with all those things, and it maybe makes more sense why you'd ever use that squiggly sign now. It's to add up a bunch of tiny pieces of something. So let's do the front face. We got to do this integral over the front, and now I'll write it out again. So what's our area vectors for the front face?
DA K hat.
Correct, because they're all poking out this way on the front. So DA K hat. And K hat dot K hat is
1.
1. So it's like these are gone, and I just replace them with a 1. And then I'll pull the 5 out of my integral, so I'm left with, what is the integral? Z squared dA. Okay. So how do I evaluate that? Do I have to do actual calculus now?
No.
No, that would be too mean. Because on the front face, what I notice is any little patch that I'm looking at, they all are at the same Z value. And so I'm finding the electric field at the same Z value as well. It is a Z value of 5 meters. So really, even though this looks like a variable, it is a constant as far as this integral is concerned. This is really just what is 5, integral over the front of 5 squared, so 25. And then all that's left inside the integral is dA itself. And this is telling you to add up all the little dAs on the front face, and that will give you the total area of the front face, which, since the cube has an edge length of 3 meters, that's like the length of any individual edge. The area of a face is 3 by 3. So left with 5, 25, and then 9. And that comes out to what, 125 times 9, 1225, maybe?
1125.
Okay, I almost did it. Okay, so pretty large flux through the front, and it is positive, which is what we guessed originally. And then through the back face, almost the same thing, except what? 2 things, really.
It's
Yep, negative DAK hat. And then what else is different on the back face compared to the front face?
The value of Z.
Yes, on the back face, it is now, you can barely see it with everything I've drawn, but Z equals 2 on the back face. So it's constant, but it's a different constant. So this will be 5, Z equals 2, I square it, integral over the front of dA, and then there's a negative now as well. So that's negative 5, 2 squared, area of the front is still, sorry, back face for this. It's still 3 squared though, and so we should get for this 36 times 5, 180, negative 180. Look, negative flux through the back face, smaller than what we got through the front face. And the last question is, what is the charge enclosed by the cube? So if I see that with a question like this, I know I automatically got to do the dirty work of all this first, and then I can put it all together. So to finish out, how do I finish this out?
You add them all together.
I add them all together to get the net flux. That's telling me overall how much electric field is passing through the entire cube. So I just write that as phi. It's add up all the individual ones, but we're just left with 1225 and negative 180. So that's going to be, let's see, 1125, 1105, 10, 1045. Oh, I did it again, didn't I? 1125. So that'll be, is it 945?
That's right.
Okay. And so how does that relate to the enclosed charge?
It would equal Q enclosed over epsilon naught, right? So you multiply both sides.
Correct. So Q enclosed is epsilon 0 times 945, and epsilon 0 is the 8.85 times 10 to the negative 12. I have no hope of doing that in my head, so whatever we get is whatever we get.
8.36 times 10 to the negative ninth.
Okay, that's 10 to the negative ninth, and let's see what the answers say once I can get this out of the way. Okay. So those are pretty algorithmic. The only tip I can really give is that one at the beginning of trying to sketch out the vector field. If you get a little bit confused on that, it is easy to do because you're not as used to drawing multiple vectors for the same object, in this case, the electric field. But it can help you to check all of these integrals because it's easy to lose negatives and other kind of small algebra stuff if you don't do that. Okay, what other questions?
Could you also do the 32, the rectangle one as well, just for the charge, just to find the charge?
Okay, I can set it up. I may not do the whole thing because it is very similar. The only real difference is the area of the faces. Now you just got to be careful that the area of that face is not the same as the area of this face. And so when you do the integral of dA bit, that is the only thing that changes, is what does integral dA come out to. But I would sketch out my vector field. So I see that it has an x component that doesn't change. So every electric field vector will point somewhat along the x direction. There is no y component, so none of them point in the y direction. There is a z component, and it grows as I move in the positive z direction. So I would think at z equals 0, which again is this back plane back behind the box, they'll start out with just that x component. But as I move forward, meaning along the z-axis, they'll start to sort of stretch towards that z direction because they start to get a non-zero z component. And if I move even further in the z, they stretch even more towards z. So my field would look something like that, and then same thing as I move up in the y direction. This is the same thing they do for wind. You can find graphs of like wind. It's sort of like the AccuWeather plots for temperature, but it's a vector field instead. My flux, I would still kind of guesstimate in the same way. I'm going to say it's 0 through the top because none of those are poking in the y direction. Same for the bottom. None of those field lines are passing through the bottom. They're just running parallel to it. I do see flux on the right-hand side because I see some arrows sticking out of the right-hand side. I would expect a positive flux on that side, and generally sticking into the box on the left side, sticking out of the box on the front, sticking into the box on the back. And then I would set up my integrals in the same way. The only thing for this one that I would see is, again, that area thing. Really, that's it. The rest is the same. It's just if you're on the front face, z is 5. If you're on the back face, z is 0. Nothing else really makes it differ that much from the previous question. Do you want me to continue through it or jump to a different question?
I have another question.
Okay. So first, Chinoso, because you were asking about this one.
Yeah, you could speed through with the solving it out, so I could see how you could find the charge. It was mainly the charge that I was having issues with.
Okay. So skip the top and bottom because I know there's 0 already. For the left, it will be 50j hat plus 6zk hat dotted with negative daj hat because that's along the y-axis. And so negative 50 integral dA on the left face. On the left face, it's that face. So it is 5/2. Negative 500. Right, for the right face, same deal, except positive dAj hat. So without going through that too much, I'll know that that will be positive 500 instead. Front face is k hat. And so that's 6 integral z dA. And on the front face, z is equal to 5. So this is 6 times 5 times the area of the front, which is this face, and it is 3/2 instead of 5/2. So that's 180. And then for the back face, it is the same thing, except I'm evaluating z on the back face. So 6 times on the back face is 0. And so I end up with 0 for this. And that makes sense in hindsight because on the very back face is where I was saying these had no z component. So if I looked at that more carefully, I'd see they're not actually poking into the back, they are actually grazing along it. So really only flux through the left and right faces. And so we get negative 500 plus 500, oh, and the front face as well. Plus 180, so that's my net flux. And if I multiply that by epsilon 0, I should get my enclosed charge, just like with the last problem. So what do we get for that?
1.59 times 10 to the negative 9th power.
Okay. And in the solutions, yes. Okay, so almost the same thing. It's just calculating those areas that was different because it's 3/2 there, and it was 5/2 here because the faces are a little bit different sizes for this cube. It's not a cube, I guess. Does that answer your question?
Yeah, that answered my question. Thank you.
Okay, I just wanted to go through that one fast because those questions they can take a while, and I didn't want to belabor it. So who had that other question a little bit ago?
Oh, I did. I was working on the review, and for question 1, I got B. I'm not sure why the answer is C.
This one's tricky. It is because induction is easy to forget. But I kind of treat this one like it's a logic puzzle. So you got to look at the steps, and it's sort of like, I don't know if y'all ever as kids did those ones where you're saying, this guy works in building A and wears a red hat and whatever, that kind of thing. And you're trying to find like what each person does and where they work and all that. I read it like that. So I see first that ball A attracts B and A repels C. That tells me two things. A attracts B, so they are of unlike charge. I don't know what that charge is, though. Or it could technically tell me that only one of them is charged, and then they're attracting through induction. So I got to keep that in my back pocket for a second. But then I see that A repels C. You don't get repulsion from induction. No matter what the arrangement of charge is, you always end up attracting the can or whatever it is. So because A can repel something, it definitely does have a charge. And so A has a charge. B is technically still could be uncharged and just attracted by induction. But these are like charges. Okay, I move on to 2. Ball D attracts B, and D has no effect on E. What's the only way that they could have no effect on each other?
They don't have any charge.
Yes.
Okay, that makes sense now.
Yep. Because even if just one had charge, it could attract the other, or would, I should say, attract the other through induction. And so that says D has 0 charge, E has 0 charge, and then B must be the charged object if it's attracting to D. So then we can close it out by just saying negatively charged rod attracts both A and E. So A must be positive to be attracted to it, and that means B must be negative because it's attracted to A. C must be positive because it is repelled from A, and then D and E are both 0.
Thank you.
Yep.
I had confusion on number 3 because I got C for number 3, even though the answer is B. So I'm like a little confused about that one.
So that's still induction. It's that if I have an uncharged insulator in class, our uncharged insulator was bits of paper. I bring a charged conductor near. I used a PVC pipe in class, but I could have used a conductor instead, like a metal rod. If I find that if I have that the conductor is charged, it will still attract the bits of paper, even though they are technically neutral because of induction. And in this case, it's an atomic level induction. The electrons will tend to spend a little bit more time on the side away from the charged rod when they're orbiting their individual atoms. And that means that it's like I've got more positive charge on the side closer, more negative on the side farther away. And so the closer side is attracted, the farther side is repelled, but less because it's farther away. And so the paper jumps up to the charged object. That is why the answer is B, because the metal rod attracts the paper, and then Newton's third law says the paper also attracts the metal rod.
I'm sorry, could you explain why in question 1 the
Yes.
ball D is 0?
Ball B isn't 0, it is negative.
I meant to say ball D, sorry.
Oh, ball D, okay. So if we think about the possible interactions that can happen, it's you got positive, negative, I guess negative, positive, but that'll be the same thing. Positive, positive, negative, negative, 0, negative, 0, positive, and then those flip-flopped as well. And then 0, 0, so no charge on either thing. If we see this, that's attracting, also attracting, repelling, repelling. It's these last 3 that are a little bit trickier. So even though 0 charge is on one of the 2 objects in this case, because of induction, we can still see the 2 things attract each other. So they will still actually be attracted, as will they in this case. The only case where absolutely nothing happens is if both objects are uncharged. And since D has no effect on E, that's the absolutely nothing happening case.
All right, thank you.
All right, so the questions I've gotten questions about are 20, 24, 30, and 36. And then a couple things about rings and disks. So for 20, a charged oil drop with a mass, that's M, is held suspended by a downward electric field of 300 newtons per coulomb, that's E. What is the charge? So that's Q on the drop. So I've got a downward field, and I've got a charge that's being held suspended by it. And I don't even know if it's positive or negative. They haven't told me that. I can figure that out by saying, though, if it's suspended, it must experience a balancing of forces. And so we have weight acting on this charge. We usually can neglect that, but if we're talking about something sitting in place, the only way that can happen is if there's a force in addition to the electrical force, and the only one here is weight. So we're talking about a field that is just capable of balancing the weight of this charge. The weight is mg from physics 1. But if the forces are balancing, that means the electrical force on the charge must be this way, upward. And so that already tells me something about this charge. Is it positive or negative?
Is it negative?
It's negative because negative charges are the ones that feel a force opposite the direction of the electric field. Okay, so it's a negative charge. I figured that much out. Now I can figure out the size of that charge, the magnitude of it. To do that, I can go back to, this would be Newton's first law. The net force in the y direction is 0 because it is suspended. But I can also calculate that net force as the electrical force upward minus weight downward. And so I get this equation. But the electrical force in magnitude is charge times electric field. So the magnitude of that charge is mg over E. And 300 for that. And the answer is whatever it comes out to, but I should add in a negative for the actual value of my charge because I found that from my picture. So negative whatever that number is. All right, so that's 20, 24. Uniform electric field, same magnitude as earlier, makes an angle of 25 degrees with the dipole moment of an electric dipole. I'd start drawing a picture here. It doesn't tell us anything about the absolute orientation of the field, meaning up, down, left, right. So I'll just pick a direction, say to the right. It's uniform. That's how I know to draw my field lines evenly spaced. Makes an angle of 25 degrees with the dipole moment. So the dipole moment points from the negative to the positive charge. They're saying this field makes an angle of 25 degrees with it. So negative and positive, and that's my dipole moment vector, points negative to positive. So 25-degree angle between them. If the torque exerted by the field has a magnitude as given, so torque is tau, what is the dipole moment? Dipole moment is P. So the torque on a dipole, this is a given equation in the equation sheet, which this is the exact one you'll get on the exam, unless I made a mistake somewhere that I need to fix by Tuesday. The torque on a dipole is dipole moment, electric field strength, sine of theta. And I am given all the ingredients I need for that. I'm given the electric field, I'm given theta, I'm given the torque. The only thing I don't know is P. So P is torque over E sine theta. There was a negative here, and I could put it, but it gave us magnitudes, so that means ignore signs. And whatever number I get for this would be the size of my dipole moment vector. So how about that? I've also got 30 and 36 on this list that I was asked about, but in the meantime, are there questions from anyone currently here?
I do have a question on number 4, but you can do that after the email if you
Okay.
want.
All right. So 30 is a quick one. Particle with charge 5 microcoulombs, that's Q, is placed at the corner of a cube, which is kind of an interesting new description. We haven't really seen any problems like that. But it's okay. So we place it at the corner. What is the total electric flux through the cube? Well, if it's a particle, it's a point charge, it's sending out field lines in all directions. And so if you look at this like the other problem with the cube where we were doing all the integration, you're going to have a bad time because you have to find the angle this electric field makes with each face of the cube, right? For any little area vector, what is the electric field at it? And that's going to change for pretty much every little area vector because the direction of the electric field is different everywhere. It's radial, so it points in all directions. So that's probably not the way to go about this one. Is there a easier way to find total electric flux?
Could you somehow write it as I and like I plus j plus k or something?
I could, but y'all are forgetting Gauss's law.
Charge over epsilon naught?
Yeah. So I can think of this cube as a Gaussian surface. It is a thing enclosing that charge, because if it's sitting at the corner, it's inside the box. And so the flux through that box, no matter what, is equal to the charge inside it over epsilon 0. So I'm given the charge inside. And this is epsilon 0. And that's it, whatever that is. So what seems like a really difficult problem is actually a really easy problem with Gauss's law. So that's 30, 36. We've got a capacitor. We are given the surface charge density. So that's sigma on each plate is that. Point P is located this distance away. So for distance, we usually use D or X. They asked about 36. If I put a certain charge there, so that's Q or Q0, just kind of depends, is placed at P, what is the force exerted on it, including direction? Okay, so let's start with the direction bit. It's a positive charge. Which way will it feel a force in between those two plates?
Down,
Down. What makes you say so?
because it's going to be attracted by the negative plate.
Absolutely. The other way we could see it is field lines. They point from positive to negative. And a positive charge always feels a force in the direction of the electric field. Either is correct, that or attracting, repelling. So the direction is downward. And I know to find the force on a point charge, I take the magnitude of that charge and multiply it by the magnitude of the electric field where the charge is sitting. So I need to find the magnitude of the electric field, which was the problem for 35, but we can start from here with it. This is a parallel plate capacitor. There is a definite expression for the electric field for a capacitor, and it is the surface charge density over epsilon 0. And that does not depend on distance. The field is uniform between the plates of a capacitor, so this number was a red herring. It's not actually helpful. If we solve for the force, which I've already got set up to be solved for, it's 2 times 10 to the negative 5. Sigma was 8.8 times 10 to the negative 8. That rolls off the tongue. And then epsilon naught is 8.85 times 10 to the negative 12. And that force is whatever it comes out to. Okay, so those were the 4. Any questions on those or a additional question? I think it was 4 was the next one.
Yeah. Also, I forgot to say, could you also discuss 5 as well?
Sure.
After those, could we go over 14?
Absolutely. Okay, so which of the following is not a possible value for the electric charge on an object? This is that thing of which one's not a multiple of the electron charge, which one is 1.5 electron charges or 3.27 electron charges, just not a whole number multiple. And so the electron charge is 1.6 times 10 to the negative 19. It's negative for E itself, the fundamental charge. We usually mean the magnitude, but for the electron charge, it's technically negative E, so negative this. But this question is really just saying which of these numbers is not a multiple of this number. How we can do that is take any of these, they would be our charge Q. Any charge should be a multiple of the electron charge. I can find that multiple, what the number of electrons it is, by solving for n, that is the number of electrons. And then I'm just left to take each of these numbers, divide it by the electron charge, and see which one does not spit out a whole number. So I can do that real fast. If I do A, I get 0.5. So it's A. It's saying you need half an electron to get that charge. And it makes sense because that's the only one smaller than the charge of an electron. It's 10 to the negative 20 instead of negative 19. So answer is A. If you did B, C, D, and E, you should get whole numbers for each of those. I guess it would be 5, 50, 500, and 5,000. If I mathed right. Does that explain that one?
Yes.
Okay. And then 5, two small charged objects repel each other with a force F when separated by a distance D. In terms of F, if the charge on each object is reduced to 1/4 of its original value and the distance between them is reduced to D over 2, the force becomes. Okay, I would sketch this out. Two charged objects repel each other with a force F. That force is the same for either one, Newton's third law. They're separated by a distance D. But then we change that. So this one had some charge Q1, this one had some charge Q2. But now we take a quarter of that. So Q1 over 4 and Q2 over 4. And we also reduce the distance between them to D over 2. I want to know what is my new value for F. So how would I calculate the force in the first part?
Coulomb's law?
Yes, they're small charged objects. Point charge would be a little bit more explicit about it, but they're saying that they can be treated as point charges, little compact amounts of charge. So Coulomb's law is K Q1 Q2 over, in this case, D squared is the distance. I'm comparing that to the new situation where now it's Q1 over 4, Q2 over 4, and D over 2 squared. So that's K, Q1, Q2, the 2 over 4 bits of it, that'll be 16 in the denominator, and then D over 2 squared is D squared over 4. So that's K, Q1, Q2 over 16 over 4 is 4. So that's 1/4 K, Q1, Q2. Oh, that shouldn't be D2, it should be D squared. D squared, or 1/4 of what it was originally, 1/4 F. Okay, so F over 4 is the answer to that one.
Thank you.
And then it was 14. Was that the next one that there was a question
Yeah.
about? Okay.
Yes.
All right, two charges are located on the x-axis. When I read a problem like this, I don't really care about the numbers if it's an electric field problem. I just care about their signs. So I'm looking at that's positive, 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 negative. And I put that on my picture immediately. Positive, 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 negative. I want to find the magnitude and direction of the net electric field at the origin, meaning right there. So to find the direction of each individual electric field, I imagine there's a tiny little positive charge right there, my test charge Q0, and I see which way it would be pushed or pulled by the other charges. And it is important to remember, because I see this a lot, what matters is what happens to this imaginary little test charge, not what it does to everything else. So sure, it would repel Q2, for instance. It would push Q2 to the left, but that's not what matters for this. What matters is that Q2 would push Q0 to the right. So that would be the field of Q2. Let's label these. That'll be E2. Q1 would push a little positive charge sitting at the origin to the left. Q3 would push a little positive charge sitting at the origin down. And Q4 would attract a little positive charge sitting at the origin towards it. That's E4. And my picture makes it seem like they all cancel. I just didn't draw them to scale because I don't know their scale until I calculate E1, E2, E3, E4. So that would be the next step. I do net electric field in the X and Y, and you can make a table for this if you want, where you would say X, Y, and then which field you're talking about and fill in your components for each. I'll just write down the equation we would get at the end of all of that. So I would get in the X direction, E2 to the right, E1 to the left, so negative, and then E4 up, E3 down, and then only at this point would I calculate E1, E2, E3, and E4 with Coulomb's law. So they called it X1, so I could write X1 squared for that. And then two squared, E3, Y3. Y4 squared. I do notice that Q1 and Q2 are the same magnitude, and they're both the same distance from the origin, just on opposite sides. So I actually can say that E1 and E2 are equal in magnitude, so no net X component. For the Y component, I'd have to calculate a little bit. So be K Q4 over Y4 squared minus K Q3 over Y3 squared. Or I'll factor out K. It is useful to do that because it saves you less calculator work. And that comes out to whatever it happens to come out to. If it's a positive number, the net field is upward. If it's negative, the net field is downward. I get 4.4 times 10 to the 6th and positive, so upward. Let's see if that's anywhere close to the mark. 14. Aha, 4.4 times 10 to the 6th, and in the positive y or upward direction. So that's me. kind of using some tricks to make it a little bit less work. You can always just be very systematic and do each of these steps in full, calculate, make sure it's all working the way you think it will, and it'll still work out. So I'm not suggesting try and have a bag of tricks ready for the exam. You will have enough time to do it the quote unquote long way. Does that explain this one, or do you want me to say any more about it?
No, that's good. Thank you.
Okay, what other questions?
Could you do number 7? Because I was confused with with after I found like the direction, it was just, I guess I didn't know how to do the acceleration portion for this question.
Okay. If it asked you how to find the net force on the negative 1.2 microcoulomb charge, would you know how to do that?
I'll use F equals ma.
You could, if so, let's look at that. So F net equals ma. I am given the mass, so that's a check. If I want to find the net force from this equation, I'd need the acceleration, but it's asking me to find the acceleration, so I don't know this. So it's maybe not this equation just yet, but I could maybe use this to find the acceleration if I knew F net from some other means. How can I find the net force on this charge in the middle?
Coulomb's law?
Yes. So I would first say it is attracted by, I'll call this charge 1, since they are unlike charges. And it is also attracted towards this charge. I'll say charge 3. And so I would calculate F net as the one pointing to the right, and then the one pointing to the left. And then I can use Coulomb's law to actually get those values. So the distance between charge 2 and charge 3 is this distance. So I'll call that R23. It happens to equal 6 meters. I'll just put R23 here. And then K, Q1, Q2 over R12 squared. And R12 is this distance between the other two charges. And that also happens to be 6 meters because it's between -4 and 2. So I would calculate this out. I would, for this problem, factor out K and Q2 because they're common to both. And then Q3 over R23 squared minus Q1 over R12 squared. And whatever that comes out to when I put in this for Q2, this for Q3, and this for Q1, and then 6 meters for both of those distances, I should get the answer I need for the net force. The final step is to use Newton's second law to divide that net force by the mass of the object to get its acceleration, and it will point in the same direction as the net force. So I would expect to the right.
Okay. Could you also do 8 real quick as well?
Okay. Which of the labeled arrows gives the correct direction of the net force acting on the charge at the upper right corner? Okay, so I need to find the net force, and that means I need to find the force due to every other charge. So I'll call this charge 1, 2, 3, and 4. You could call them any numbers you want. There's nothing special about calling that first one 1. I just is convenient. Okay, so let's see. Charge 2 is positive, so it would attract charge 1. Charge 3 is negative, so it would repel charge 1, but it is further away than charge 2 is because the diagonal, this distance, is longer than the side of a square because Pythagorean theorem or triangle inequality. Lots of justifications for that, but since this is the hypotenuse of that triangle, it's the longest side. And that means the force 3 exerts on 1 is a little bit weaker than the force 2 exerts on 1. And then the force that 4 exerts on 1, it's going to attract charge 1. So it'll look like that. And so I have to add those 3 blue vectors to get my net electric force. And I might do it if I'm trying to do it geometrically, meaning not try and get into the nitty-gritty algebra, although you could to end up proving this. I might say, I'll look at this one and I'll look at this one. To add those two, I could either use parallelogram rule or tip to tail, but with the parallelogram, I get that the net force is that vector. That is being opposed by F3 on 1. We said F3 on 1 is weaker than either of these two individual forces because they're acting from a larger distance. So this is a smaller force than the net force we get by adding the other two. And that means that the overall net force from all 3 vectors points down and to the left in the direction of the net force of just this one and this one. So the correct answer is B because of that difference in distance. So there's some in the homework for rings and disks, but I'll go to the textbook once I can. This one was what I based the question that's in the notes on. I modified it some. You can really expect questions like this, just sort of cookie cutter, like I tell you all the things you need to calculate the electric field. That's the one case, or the other case is something like this kind of problem, where you have to think about the directions of the fields as well. So maybe I'll do that one, because it's a little bit more involved than this one. For this, you would just say, well, for disk, electric field is sigma over 2 epsilon 0 1 minus c over square root z squared plus r squared. This is r. This is sigma. This is z. And they're asking, what is e? It's plug and chug. But this one up here, two parallel non-conducting rings with their central axes along a common line. Non-conducting seems important. It's not really that important. That's just to say that you don't really get a lot of induction effects that would shift charge around so that it's not uniform on the two. You can treat them as sort of these things with fixed charge uniformly distributed over each surface, and we know how to deal with the uniformly charged ring. So ring 1 has uniform charge Q1 and radius R. Ring 2 has uniform charge Q2 and the same radius. The rings are separated by a distance of 3R. The net electric field at point P is 0. What is the ratio of Q1 to Q2? If the field here is 0, I got 2 options for the way the field points for either ring. Could be away from each if they're both positive. Could be towards for each if they're both negative. Could be away from one towards the other if it is one's positive, one's negative. The only situations out of those cases where I could get a cancellation of fields is if both rings have the same type of charge. If ring 1 is positive and ring 2 is positive, for instance, the field due to ring 1 points that way. Field due to ring 2 points the other way, because that's how they would each be pointing away from their respective rings. If both were negative, it would be the same sort of thing, but both towards. In either case, they're in opposite directions, and that's the only way you're going to get them to cancel. So that means Q1 and Q2 have the same sign, and so I'm expecting a positive number for this, whatever those charges are. I don't know if ring 1 and ring 2 are both positive or both negative, but it's got to be one of those cases. So that's the first thing. The next is that E net is 0, and it's E1 minus E2. And I can write the expression for the electric field for each one. Believe it's QZ, so this will be Q1 over 4 pi epsilon 0 z squared plus r squared to the 3/2. And then same for E2, but this is Q2. And then for Z, it's just where is my point I'm looking at, point P, in relation to each ring. It is a distance R away from ring 1. So I will put R for each of these. I'm just looking at my picture to see that. And it is a distance, well, the total distance between the two rings is 3R. So this must be 2R. And so I'll put 2R for Z for ring 2. And so just put that all in. R squared plus R squared to the 3/2 minus 2r over 4 pi epsilon 0. I picked a laborious problem. I should have gone with something easier. If I simplify that out, one thing that's going to be helpful is I put these back on opposite sides. In other words, if E1 minus E2 is 0, that means E1 equals E2. And so I have Q1R over 4 pi epsilon 0. R squared plus R squared is 2R squared for the 3/2. And then on this side, 2Q2R over 4 pi epsilon 0. 2R squared plus R squared is 5R squared to the 3/2. And so if I want to get the ratio of Q1 to Q2, I'm just solving for that, basically. R's cancel, 4 pi epsilon 0's cancel. So Q1 over Q2 is whatever's left over. I got to bring this over to the other side. And so it's 2R squared to the 3/2 over 5R squared to the 3/2. So that's 2, and then I can combine these. R squareds cancel. So whatever 2 times 2/5 to the 3/2 power is, that's not a nice number, it doesn't sound like. But that's how you would look at this. It's a little bit more algebraic than what you'd expect, but it is just sort of taking the known equation for the electric field of a ring and then also accounting for the direction of those fields. So for me, a question might be more like, what is the direction of the field at point P, or is it 0? And then maybe calculate the net electric field directly, and you'd be given more information so that you can do it that way rather than this sort of messier process. All right, well, y'all enjoy the rest of your weekend. And again, email if there are any questions that pop up.